So we're going to go ahead and continue with question 3.7. So 3.7, given water vapor at 15 megapascals and 350 degrees Celsius, determine its specific volume using A, the thermodynamic table for R134A. That's just a typo there. Of course, if we're working with water vapor, we want to use the thermodynamic tables for water. So if we can just ignore that and pretend it says water there. And B, the ideal gas equation of state. So we're using this to find the specific volume. And C, the compressibility chart. So, all right, let's start with the simplest one, which is using the thermodynamic table. So this is already water vapor. We already know we're going to go to the superheated table, and we're looking for 350 and 15 megapascals. If I can find it. There we go. So here, 15 megapascals and 350. And immediately we can see, can I draw on this? Yeah, I can draw. If we go to the 15 megapascals, 350, the specific volume is given right here, plain as day, so 0.011470. So let's write that down. And of course, this is meters cubed per kilogram. And this was found using tables. Now, the other way we're asked to do this is using the ideal gas law. I'm just going to leave a note here that this is all done at 15 MPa and 350 degrees Celsius. So using the ideal gas law. So what's the ideal gas law? We can say pressure equals rho RT. And of course, this is equivalent to saying pressure equals RT over specific volume, because rho is just 1 over specific volume. So solving for specific volume, we can say, specific volume is RT over pressure. And of course, to keep things consistent, we have to use Kelvin here. So 350 plus 273 always gives us 623. So V equals 623 times R over P, which is 15 megapascals. So like this, 15 million, right? Now what's R? Well, again, R is depends on the fluid you're using. So we can get that from a table if we don't know what it is. And if we go all the way up to the top, it should be around here. Yeah, we see the third column is gas constant. So if we go to water, we see we have R is 0.4615, and it's kilojoules per kilogram Kelvin. So 0. Just going to bring it up on the other screen there. 0.4615. So I'll just leave it note. If I can get the pencil going here. No idea why it's not writing. Hang on a moment. Now it shows up. Okay, so I'm just going to continue from here. We said that V equals RT over pressure, where R we just read off from the table. For water, that's going to be 0.4615, and the temperature is 623 Kelvin. And that's, of course, divided by 15 million pascals. And if you do this, we should get something similar to what we found from the table. hopefully. And it comes out to 1.9167 times 10 to the negative 5. And the reason that number is so small is because the units here are inconsistent. So you'll see the mistake I just made is this is in pascals and Kelvin, but this guy's in kilojoules per kilogram. So really, it's the numerator should be multiplied by 1,000. So my answer should be multiplied by 1,000 to put everything into joules, and then it makes a bit more sense. So then it becomes 0.0192, and that's of course meters cubed per kilogram. Okay. So how does that compare to what we had before? Well, what we had before from the table was 0.01147. So you can see there's a significant difference. We went from about 0.011 to 0.019, which is like nearing double what we had before. And why do we have this issue? Is because we're using the ideal gas equation. In this case over here, we're using the ideal gas equation to try and solve for things in something that is not even close to an ideal gas, right? So the ideal gas assumptions basically are that the gas is not at a very high pressure temperature. But in this case, we're at both of those things are at 15 megapascals, 350 degrees Celsius. Relatively speaking, it's not really an ideal gas. So we don't really expect that the ideal gas method will give us anything remotely accurate in this case. But what we can do, and this leads us to part 3, or part C, if you want, is we can use the compressibility charts to try and get a better sense of what V3 is. So if you didn't have the water table and you only knew the ideal gas law, you could kind of correct the ideal gas law by using the compressibility charts. Okay? Now, to use the compressibility charts, what we're basically doing is we're comparing the temperature and the pressure of water, or of whatever you're working with, but in this case, water, to the critical temperature and the critical pressure. And you're going to use that to get what you call a reduced pressure or a reduced temperature. Okay, and we're going to see how to do that in a second. But basically, from those reduced pressures and temperatures, you're going to be able to find a factor that's going to correct your ideal gas answer. So we're going to put this on the back burner for a second because we are going to use it, but we need to figure out how we're going to multiply it in order to get something more accurate. So to get the compressibility, well, we have to look at the compressibility chart for water. It's a general compressibility chart. It's not really for a specific material. But in this case, we're working with water. And if you look at the bottom right, you see this Nelson-Obert generalized compressibility chart. So you have these equations. Now we're given the pressure and the temperature, so it's most efficient for us to work with pressure and reduced pressure and reduced temperature. And you see that reduced some quantity is just that quantity divided by its critical value. And these critical values are, of course, dependent on the material or the fluid you're working with. So let's find our reduced pressure and temperature. So, of course, we need to know the critical temperature and pressure of water, and we can get that from the right section here, this table, and we see temperature and pressure in the first two columns. And we can see that the temperature and pressure, and of course this is indicated in megapascals, is 647.3 is the Celsius or Kelvin, and 22.09 megapascals. Okay, so let's see what that means. I'm just going to write on here for a second, but we're told that the reduced temperature is the actual temperature that we have, which is 350 plus 273, so 623. divided by 647.3. And you see that it's 623 divided by 647.3. It's getting very close to the critical temperature. And the closer you are to the critical temperature, the closer these TRs and PRs are to 1, it means the less valid the ideal gas law is going to be for you. So if we do that, we'll find it's 0.96. So there we go, getting very close now to 1. 0.96, and PR is going to be, we'll just keep things in megapascals, is 15 over 22.09. 15 divided by 22.09 gives us 0.68, right? 0.68. So let's keep these numbers in mind, 0.96 and 0.68. Okay. And if we go back to the compressibility chart, now we can actually get to use the chart. So how do we read this? Well, clearly we have on this axis the reduced pressure, right? And then we have this thing Z called the compressibility factor, which is what we're trying to find, because that's the factor that we're going to multiply our ideal gas version by. Okay, but we have to find what our compressibility factor is. And you see these pink solid lines, they're labeled as TR, which means reduced temperature. So any pink solid line is a line of constant reduced temperature. So how are we going to do this? Well, we know our reduced pressure. So our reduced pressure was 0.68. So we know we draw a vertical line around, how is this graduated? 0.68, so about 0.7. So if we draw a vertical line like, that wasn't very good. We draw something around here, okay? So we'll do this really rough, but it's just important that you understand the overall method here. So that's around 0.68, and that's our reduced pressure, which we calculated, and our reduced temperature is 0.96. So unfortunately, they don't give us a line for that, but that's close, pretty close to 1. So if we look around here where it intersects, and here, because this is the line here, this pink line is TR equals 1. Sorry for my shakiness there. But where this line intersects our vertical line of reduced pressure, that's what we're looking for. And if we just read off the graph what that corresponds to, it's about 0.7 on the compressibility factor chart. So all we do is we take this 0.7. This is everything we did was just for this. We're going to say it's 0.7 times the ideal gas version, right? Which is 0.0192. So if we do 0.7 times 0.0192, we'll find 0.01344. So not perfect, right? But much better than the other estimate, right? Compared to this guy being the actual value experimentally, right? So it's not perfect, but it's close. And again, why isn't it perfect? Well, we're using a chart which could have probably been read a bit more accurately, is probably the main reason. But yeah, that's mainly it. So what did we do? Just to summarize, to get the compressible version, we looked at the reduced temperature and reduced pressure, right? Just to see how close we are to the critical temperatures and pressures. And from those two bits of information, we read off the chart our Z value. So that's the vertical axis. And that Z value is used to multiply the answer you would get from pretending it's an ideal gas, which we know it's not. But yeah, this is what you would get by doing that. All right, so thank you very much.